And we are back. So welcome back. Let's continue. So I hope you could observe the how beautiful this query is, group by, order by, and so on. Quite classical. This is called a histogram in data science, right? It's a histogram, and so the goal is to plot such data, for example, with matplotlibs and so on. So you could export that as CSV, for example, and then plot it in a Jupyter notebook. Now, just when I said flower expressions are like select from where, I just want to give you a taste of that, because select from where does selection, projection, aggregation, and so on. So imagine we have these two data sets, products and stores, and you can join them because the store in the products points to the ID of the store on the right, right? So this is how they belong. For example, the first one, the TV store one, so that would be Switzerland. So aggregation, selection, projection is easy, right? Selection is with the where clause. Projection you can do by putting whatever keys you want in the output. That's projecting to them. Aggregation is with a group by. So here we just group by type, count the number. This group by is 0815, right? This group by is the same as SQL. You could have that in SQL too, right? You group by the type and then you count or aggregate any other keys. So this one is vanilla. The other one I showed you, this one, no, this one is also actually SQL-like. It's the other one that we had before. Yes, this one would be the group by that you cannot do in SQL, right? But let me come back. The one that I show you here is just like in SQL. So you see, it does whatever SQL can do. Then we have joins. Do you remember that the joins in SQL, there are several ways to do them. You can either put two tables in the from clause and then use a predicate in the where clause, or you can use a join clause in SQL. Well, if you want to join two data sets in JSONic, just use a double for, and then where, right? So for every product and every store, where they match, and there you go. Then you have associated them, and then you can go on, in that case, outputting the type and the country. That does a join. For whom is that clear? Right? But you don't have to worry, at the exam, there's only one file, right? So you won't have to join anything. Yes? Was there a question on Zoom or all good? Okay. Then some of the cool things you can do with JSONic, and again, that's something you cannot do with SQL. SQL is for normal forms, right? So the data is highly structured and spread into tables. But what we want to do in the beautiful world of big data is denormalize the data, right? So for example, what if I want to list the stores and inside every store, I list the products? You agree that data is no longer in the first normal form, right? The data you see here. It's no longer atomic, there's a nested array. And the way I can create it is, for example, I iterate over the stores, and then I find my products with a variable P that will be bound to a sequence of products. How do I find them? Well, I have this subquery in the product. I look at the products right here, but I only take those whose store matches the store that I have here. It's matching them, right? So now, for every store, here I have the list of products that are in that store. And then I return the country of the store and the products that they are in there, right? For whom does that make sense? Right? So that is a kind of denormalization where you can nest, build something that is nested. All right? What is magic is that it might look inefficient, because you might think if you use your Python hat or your imperative hat, you might think, okay, we iterate on the stores, and for every store, we scan through the products. This is not going to happen. The engine is smart. The engine will figure it out. Because what the engine will see is that you are, in fact, matching the stores and the products, and internally, in Spark, it will actually do some sort of join. It will detect it. The user will just notice that it's actually fast, even if you write the query like this. Right? So that's the power of data independence and of a functional declarative language, is that you give enough room to the engine to optimize, to parallelize, to figure out the best way to execute this and deliver to you the results in the fastest possible way. Quick parenthesis on types, because we've seen types a couple of weeks ago. They exist, and that shouldn't surprise you. We have integers, booleans, arrays, objects. So that's the XML schema and the types for the atomic values and then array object. The question mark plus star should normally not surprise you either, because that also I mentioned a couple of weeks ago in the validation lecture, right? I told you question mark is 0 or 1, plus is 1 or more, star is 0 or more, right? So you know what they mean. But do you see that in JSONic, we return sequences of items, right? So that's a natural thing to do, to have types that look like this, right? So the first type means a sequence of one integer. The second one means a sequence of one Boolean, possibly empty. The third one means a sequence of arrays that is non-empty, plus at least one. And the last one means a sequence of objects, possibly empty, right? These are my types. And I can use the types for every variable. Optionally, I don't have to do that, but if I want, I can also include a type in my variable. So path is a string, events is a sequence of objects, logins is a sequence of strings, and so on. Count is an integer, and so on. It actually is good for debugging or catching any issues, right? If you add the types and the type doesn't match, you will get an error. So it's very good. It helps you to write queries if you have a doubt and you want to have some control of the kinds of values that are returned, okay? So all I did here, I added some types, and that's pretty much it. You also have a few perks, just like in Java or other programs. You can test if some expression returns a specific type. So instance of will tell you, right? Instance of integer star here is going to return true or false. False, right? Because foo is not an integer. So this is going to return false. It tests whether that is a sequence of integers. You also have functions, but you don't have to worry too much, just so you know that they exist. That you can declare them, and then you can specify the types optionally, and you can specify the return type optionally, and then in the body of the function, you have an expression, right? This is already advanced, these sort of things. Coming back to my histogram, I just wanted to show you that you can, in fact, take this output that I said is a relational table here. You can create a schema that is the JSON syntax. You can declare a type using a JSON schema. Commits is an integer, count is an integer, right? And then you can validate this. This here is going to be validated against a sequence of this. So this checks that it's going to be a table with two columns, right? A data frame, in fact. You remember, valid JSON. If the schema is not too exotic, that is a data frame. Well, in fact, when you do this, RumbleDB will in fact create a data frame. And once you have the data frame created in this way, you can use this output format parameter and say Parquet, CSV, whatever you want. So let's do it in CSV. Header true to make sure that it has the headers in there. Number of output partitions just to coalesce it to just one file. In the output, overwrite yes, just to make sure if you already wrote it before and so on. And that's the directory to which you write, right? And it's that simple. You put that in a file, run query.jq, name of the file, and it just will create the CSV file. And then I did it. I opened it in some software, can be Excel, Apple number, anything. And yeah, that's how you can interact with the ecosystem in this way. Which brings us to how it is done. Because as I said, the language, just like SQL, is functional and declarative. What it means is that the query you are going to write on your laptop for 100 objects that take a few kilobytes is the same query that you are going to write on a cluster of 10,000 machines with a petabyte of data. The same query. The only thing that changes is what's happening behind the scenes at the execution level. And RumbleDB can do both. It can do it on your laptop. It can do it on a cluster. It's going to take care of it. And so it's interesting to see how this is actually working, because again, that's the beauty of data independence. So I'm going to give you a short 101 of the architecture of a query engine like that. It's pretty typical. What you will see here on the first slide is a typical way that query engines are implemented. So here there's nothing too surprising. So the first thing that happens when you receive a query that the user put in their Jupyter notebook or in some file is you parse it. Just like you parse JSON, you parse XML, you can also parse JSONic, right? You can parse a query. Well, there's a whole history of developments in computer science and even lectures called compiler design, compiler BAO, that are given at ETH on how to do this, how to implement such programming languages and so on. And in fact, what computer scientists came up is the idea to convert the query to a tree that is called an abstract syntax tree. It's just a tree representation of the query. It's quite complex. It involves what's called a context-free grammar and some rules and so on, details of which I'm not getting into. So you have to take my word for it to just believe me that when you have a query like that, you can convert it in some abstract syntax tree. If you look at the query and the abstract syntax tree, it might even make sense somehow, the way that it is mapped, right? So the count would be the root of the tree. Then we have a flower with the 4 on the left, the return on the right. 4 iterates on I on JSON lines of file.json, return .field $i, right? It's quite intuitive. So we have techniques that do that in a very good way. We even have libraries that help you do that. So that's the first thing that RumbleDB does, is it takes the query and converts it to an abstract syntax tree. But the abstract syntax tree can be very complex and redundant and not very clean. So the next step is to clean it up and to convert it to a better, cleaner, more compact representation called an expression tree. And this is where we have the Lego game, because at that point, we have a tree of expressions, right? And this is why it's called a functional language, is that you can see every one of these expressions as a mathematical function, right? That creates some output based on some inputs. But the cool thing, what characterizes a functional language is that even though technically these are mathematical functions, in the language, you barely see any parentheses. You might see some of them when you open the file and so on, but when you use addition, multiplication, and so on, you really don't see so many parentheses. Compared to an API like the JavaScript API in MongoDB, you will see many more parentheses, right? But anyway, this is the reason it's called a functional language. We get at some point the expression tree. Computer scientists love trees so much, right? So expression tree. And then this is where the optimizer kicks in. So the optimizer is some code in the engine that looks at the expression tree and thinks, how can I improve it? How can I find the spots where the user might have written the code in a not so efficient way? And it's okay because it's a declarative language. And then the optimizer is going to rewrite the tree. Keeps rewriting. An example of the sort of things it can do is that it can spot a let clause that defines a variable that is not used anywhere, right? So in that case, it can just remove it from the tree. And then you get a smaller tree, it doesn't have the variable anymore. What else can you have as an optimization? For example, you might be opening a Parquet file that might have billions of objects, but you have the schema, of course, because it's a Parquet file. And then if you look at the query, you basically realize that even though the Parquet file has a schema with 100 columns, the query is actually only reading 2 of these columns. It's not reading everything, it's just using 2 columns. Do you see that then the optimizer can detect that and only read from disk the 2 columns that it needs, and not even read at all the 98 other columns? This is the sort of things that you can optimize. And that is done by putting in the tree the instructions that you only are to read 2 of the columns. That is the benefit of Parquet, right? If the data is in the JSON format, you cannot optimize in this way. That can really be done because of Parquet having this columnar structure with the way that it organizes the columns. These are just a few examples of many things that you can do. There's functional inlining and so on and so on. It's actually never ending because that's a problem that will never be fully solved. It's an undecidable problem, right? So you just keep having humans who keep thinking of more and more optimizations that you can detect. But anyway, that's going to compact the tree and make it simpler and cleaner and more efficient. And when you're done optimizing the Lego game, you turn that tree into what's called an iterator tree. this is what is executable. That is the one that you can now run on the cluster. And I'm going to go into the details of these iterators, how they work, but it's still a very similar structure. But the difference between the two is that the one on the left is only a representation of the query. The one on the right contains computer codes that knows how to execute this. These are the iterators. It will become clear why it's called an iterator. And so when we are at that point and you look at the iterator tree, what you have to see is that most of these iterators that correspond to expressions, they return sequences of items. So whenever you see this arrow that comes out of an iterator, imagine that you can pull items out of it. You pull out a sequence of items, but just getting an item, getting an item, getting an item. But not everywhere, because some of the nodes in that tree are actually not expressions, but they are clauses, right? The for is a clause. So here, of course, the for clause is not going to return a sequence of items. It's a clause. It's going to return instead a stream of tuples, which we now know is in fact a data frame behind, right? We are going to have a data frame for that. But anyway, that's why I put another color here, because it's a clause, it's not an expression. But everywhere else where you have an expression, the black edge here, it's basically just items that you pull out of it. And the idea is that you look at the top here, that's the outside of the query, and all you do is you pull the items out of it one by one, and this is recursively pulling the items up the tree and percolating down to in the iterator tree. Who sees that? Right? You just pull out the items of it, and the computer code is taking care of making the data flow in this way. That's how it works. Let me zoom in a little bit so you understand. So imagine that I have these JSON files, objects.json lines. I put the JSON L explicitly. You will also see it as .json very often, but .json L makes it even more explicit that it's JSON lines. So I iterate on them, and for every I extract the field. It's a pretty simple query, right? So now, how could I execute that query? Imagine it's very small. It's a small file. It only has 6 objects. So what you might consider doing for such a small file is you just load it entirely into memory, right? So you load it entirely into memory, and then you have your 5 objects, everything in memory. Then you have the for iterator. So you're going to create your data frame with the 5 associations, right? Again, everything together in memory because it's a very small file. And then you have the return iterator. And again, it's the idea of pulling the items one by one, 1, 6, 4. Oh, I have to not be too fast when I click here. 1, 6, 4, 3, 2, and so on. When you do it like this, it's called a materialized execution. What materialized means is the idea that you read the file entirely and have it, in fact, in memory. It's called, we say it's materialized in memory. It's actually there. Then you have here the materialized data frame because it is actually in memory with everything here. So it's materialized. And again, here the output might be materialized on your screen, but again, it's very small. It's only 5 items. So this is called materialized execution. It works for 5 objects. Now imagine if the file that we are reading, or maybe we have 1,000 files, have 1 billion objects. Do you see that this would be impossible to do it in this way? I would basically have to read my file, put all the billion objects in memory, then I would have to create a data frame on my laptop with 1 billion items, and then I would put a sequence of 1 billion items. I mean, most laptops today will have difficulty. Maybe a billion might still fit, so let's take 1 trillion then, right, to be absolutely sure. So you see the limits of that. If there's too many objects, that doesn't work anymore, right? That only works for the small objects. So it can take a lot of memory, and that's going to just break things when there are too many of them. That's okay, because we have another way to do that. This other way is called a streaming execution. And when I say streaming, think of Netflix. right? Or Amazon Prime or whatever, right? Think of streaming. The difference between streaming and downloading a movie, so like it was 10 or 15 years ago, you had to download the movie to your computer. Now you don't do that anymore. When you open Netflix and you start watching a series, what does it do? It just downloads the next 10 seconds, 20 seconds, right? And when you watch it and arrive towards the end, it will download the next 15 seconds, right? This is streaming. And it will adapt the resolution. If it notices the internet connection starts to be slow, the next 20 seconds it's going to download will be in low resolution. Then it sees the internet connection improves, so the next 20 seconds will be in high resolution again, right? So this is streaming, just like Netflix. And we do it exactly in this way. Streaming means that we have this file on the disk, but we only read the tuples one at a time. So field one, and then I calculate one, and I write it somewhere and so on, and forget about it. Then I take the next one, 6, I write 6, and then maybe to the disk or somewhere, forget about it. Then 4, then 3, then 2, like this. Who sees that this can go on and on and on and on and on with very little memory usage? Because I'm only processing one item at a time, right? This is called a streaming execution. This is also the reason why these are called iterator, because we are iterating over the items, we are iterating over the tuples. So it's an iterator. The way that computer scientists implement iterators in Python, Java, or some languages like that, and that's hidden from the user, is with functions that are called hasNext and next, right? You call hasNext, is there a next item? Yes, no. If there is one, then you call next and get it. Then hasNext, yes, next. hasNext, next. hasNext, next. hasNext, next. Oh, hasNext is false, then I stop. That is called an iterator API when you do this, right? And so this is what actually these iterators here are doing. They have a function called hasNext and a function called next in such a way that they give the items one by one. At every call, you get the next one until hasNext returns false. So that gives you a streaming execution. But there's still a problem, because with the first one, the materialized execution, we have a memory problem because we cannot store arbitrarily large files into our memory. Now we have a problem with time, because now we could read the quintillion items if we want it. But the problem is that we are still going to be here in 10 years. Maybe even at the end of the universe, we are still there, right? Because it's going to take forever and forever, right? The items, one by one, a quintillion, that's also not going to just work here. It's part of the solution, that's a good thing, but we are not quite there yet. Does anybody see what we need to process the quintillion or quadrillion items without needing that much time? Exactly, it's the parallelization. This is where the data center comes into play. Because now in the data center, you're going to have tens of thousands of machines, and you can just do it on all the machines in parallel. So an example here can take too much time. So of course, it's a slide. I'm not going to put 10,000 machines in there, so I only put 2. We spread the data over the machines. So the first machine takes 1 and 6. Second machine takes 4, 3, 2. That shouldn't be news to you. We've seen that before, right? It's the blocks, the partitions, the splits. We've seen that all over the place in this lecture, right? So no surprise at all. We could, in fact, imagine that this is stored on HDFS. We just take the blocks. We take the HDFS blocks, maybe with reading the last few bits remotely, as I showed you in MapReduce. And then every block gets processed by one machine. Imagine MapReduce, Spark. This is exactly what happens. In fact, this is Spark coming into play in here. And then this is done in parallel, because in that case, it's a narrow dependency, so there is no shuffling involved, and then output like this. Who understands? Right. So it means that RumbleDB, when it creates these iterators, it's able to materialize, it's able to stream them, and it's also able to do it in parallel. And it's going to just decide depending on many factors, but it's figuring it out, right? It's automatically going to figure out, oh, that's on HDFS, let me parallelize. Oh, that's local from the disk in a single JSON file, I won't parallelize, right? It's just going to decide the query looks the same. It's just internally that it's going to execute it, materialize, streaming, parallel, and so on. And of course, the cost of that is that it takes a lot of machines, but there is no free lunch, right? Well, there is one, that's the optimizer, because maybe sometimes the optimizer figures out efficient ways. So RumbleDB works with S3, HDFS, even HTTP, even though comes with a warning, HTTP is not going to work in parallel, right? Because HTTP is not a full infrastructure with blocks and so on, right? So if you read from HTTP, it's just downloading it and that's it. Local file system, it can read in parallel. In fact, it can use the cores of your machine. Even on a laptop, it can be fast, just not as much as in a data center. Azure Blob Storage, and so on and so on. Google Cloud Storage, we haven't tested, but there's no reason why it wouldn't work. So this is the place for the data lake. Then in terms of formats, can read JSON, CSV, Avro, Parquet, Root, which is the CERN high energy physics format, libsvm for machine learning, and so on, right? So this is everything it can do just with the same language, the same queries. And so to show you how it's actually working, now if you think a little bit of the execution strategies, on the top left, you see an expression that is basically the empty sequence. Well, in that case, you don't need a data center with 10,000 machines, right? It's just a simple method call. It returns internally null, and that's the empty sequence. 1 to 4, that's an iteration, but it's a small one. It detects that here there's not so many items. A data center would be an overkill for that, right? You don't need a cluster with a huge number of machines. You just use an iterator, a Volcano iterator. Next has next, next has next. So it's going to call has next, next 1, has next, next 2, has next, next 3, has next, step 4, has next, false, we stop. So just an iterator, one by one. Here, it automatically detects that it's just a simple arithmetic that only returns one item. So it will not even bother with iterating because there's only one. So it directly calls methods. Right, 2 times 3 gives you 6 plus 1, 7, right? So it's automatically figuring it out. And here it's figuring, okay, it's still a small sequence. So we have an iterator. And here we add another iterator on top that filters. So it's going to let every other item pass and every other item filtered out, right? So this is called the local execution here. Because all of that doesn't need a cluster, right? All local on a single machine. But as soon as you start reading from HDFS, so imagine the working directories on HDFS, and we read a JSON lines file, remember that the JSON lines file might not have a schema. It could be a huge mess with no schema at all. So what RumbleDB does is it creates an RDD of items. And the items can be anything, but that's fine because it doesn't need to be all the same in an RDD, right? So an RDD of items. And every value in this RDD is going to be one object, right? It's all implemented in Java, so this is in fact using what's called polymorphism in object-oriented programming, and we are going to have object item instances inside the memory. But bottom line, it's on HDFS. RumbleDB creates an RDD, and the RDD can have billions or trillions of values in there on the cluster, right? Then we navigate .countries. Remember, we have an RDDs. How do we navigate on every one of the values of the RDD inside in there? That looks like a map or a flat map, right? You remember the flat map transformation? So we can just use a flat map transformation that takes every value, which is an object, and extract the value associated with countries. That gives us, again, an RDD. And now you see the heterogeneity, because some of the values in that new RDDs are going to be arrays, and some of them are going to be strings. And that's totally fine, right? Because it's an RDD of items. The items can be whatever. Everybody still with me, right? So this is a huge mess here, the data, but it still works. Now I have this array unboxing. So I have my empty square brackets. So now I open the arrays and flatten everything that's in there. That's also done with a flat map internally. And so everything that wasn't in an array is just disappearing, that's thrown away, and all the values inside the arrays are kept. But I insist that this RDD, this flat map, all of this, the user doesn't see. The user is just in front of their laptop, in front of a Jupyter notebook, and type the query, and that's it. What I'm showing to you is completely hidden, completely automatic, completely hidden. The user does not even see Spark. They do not even see anything. But the implementation uses Spark. Now I have distinct values. Easy. It's a transformation in Spark. It's just the distinct transformation. Right? So you see, just like I have a Lego game with Spark, I can use it to build the Lego game with RumbleDB. So it's implemented for every expression. There is an implementation that leverages Spark and finds the applicable transformation to take care of it. What about if I don't open a JSON lines file, but I open a Parquet file? You know that Parquet is structured. There is a schema. It's much more compact. So what do I get out of this array? Will I get an RDD? What do I get if I open a Parquet file? I get a data frame, right? So I'm getting a data frame. That is super nice, right? I get the data frame, and then I will apply data frame transformations instead of the RDD transformations, right? It's just going to be faster. But the user will not notice the difference. It's still the JSONic language and so on. So the user couldn't care less if it's an RDD or a data frame or whatever. The user just cares that it's going to be fast. So if I summarize, whenever we have something completely messy and heterogeneous, we can just go for an RDD inside. Whenever we have something super clean, super structured, like something that you got out of a Parquet file, just use a data frame. Right? That's how it's going to work. So this is for the expressions. We can do the same thing for the flower expressions, for the clauses in there. Selection, grouping, projection, join, generic. So everything we can do there is in fact going to be implemented with data frame transformations. Why? Because just like here, a sequence of items that is highly structured can be seen as a data frame. A tuple stream can also be seen as a data frame. Do you remember the tuple stream semantics when I drew these data frames with the variable bindings earlier? These are data frames. Why is it structured? Because every column corresponds to a variable. So this is highly structured. When you look at the flower expressions, it's always the same variable in every binding. So this is highly structured. So it means that we can implement that as data frame transformations. So for example, now if I continue to show examples, I have JSON files, persons. At that point, it's an RDD. For person in JSON files person, so now I have a data frame with one column, and every value in the data frame is one object. But because it's a huge mess, I just store it in a binary fashion, just a binary representation of the object. It's okay because the user doesn't see that. It's all handled by computer codes. Then I have for, that's creating a second variable. So now it extends the data frame with the second column. Again, as a data frame transformation, a where clause is going to just apply a filter on the data frame, right? It's very intuitive. A let clause is going to create a new data frame, adding a column, and so on. And I return, and then that maps back to an RDD. But again, I insist, all of that is hidden from the user. The user does not see that. When you are on the exam typing your JSONic queries, in the JSONic assignment, you don't need to care about what's happening behind the scenes. Just type your JSONic query and see the outputs. That's it. But the secret is here. The way that it's actually implemented is here. So you see how everything is coming into place. It uses HDFS, the JSON syntax, validation, data frames, transformations, parallelism. Everything we've seen in the semester is coming into place in the implementation of an engine like this. So it all belongs together, the way this plays together. So we can implement the flower clauses as data frame transformations, a filter for the where clause, and so on, as shown right here. But then look at this one. For I equals 1 to 100 returns I plus 1. Do we need a data frame for that? Well, in big data, 100 item is something that is considered ridiculously small. So if you just want to manipulate 100 values, you don't need a cluster of machines for that, right? So in that case, RumbleDB is not even going to bother with the data frame. In that case, it's just going to iterate. It's going to take one by one, 1, 2, 3, all the way to 100, and for every one, adding 1. But it's still going to stream on that. It's not materializing the sequence of 1 to 100. Who is with me? Right? So you see, we figure it out dynamically, smartly, what's the best execution depending on the size. So this is for the clauses, either as an iteration or as a data frame transformation. And if I summarize for expressions, but it's things that I already showed you, we can use direct method calls if it's a single item. We can use iterators if it's small sequences and you just make your way through it. You can use RDDs if it's messy, nested, heterogeneous data, then you can use RDDs. If it's nested but structured data, then you can use data frame transformations. And finally, what I did not say is that there is even a feature with native Spark SQL queries. In some cases, RumbleDB is even directly able to write Spark SQL code for it natively, which is even faster. So this is the fastest that it's ever going to get compiled to Spark SQL. All right. And so what happens is that there is, when you put your query, a whole initial round of figuring it out, right? So it's scary names like we create a static context, a sequence type inference, determination of execution modes, and so on. These are just scary things to say. Before it executes the query, RumbleDB thinks and analyzes. What is the best way to execute that query? What can I predict about the execution that allows me to optimize and figure out the best way in parallel, streaming, and so on, to execute it. And once it's done that, what you get is this beautiful runtime iterator where all the decisions have been made of what is going to be with an RDD, what is going to be with a data frame, and so on. By the way, nobody asked, but I threw an acronym at you called UDF without defining it. Who knows what a UDF is? It's just a user-defined function. Remember that when I showed you the map transformation, the filter transformation, the flat map transformation, we pass a function in there, right? This lambda, blah, 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 right? When you have a filter, you pass a function that returns yes or no. UDF is just a name for that function, right? It's just a UDF. It just means user-defined. It means you write it yourself. You say a dot filter, and then you write lambda x with some predicates. It's a UDF. So you basically already knew what a UDF was. I just didn't tell you it's called a UDF, right? But we've seen them when we studied Spark when we did that. The map function and the reduce function in MapReduce could also be called UDFs, right? It's whenever the user supplies a function for a Spark transformation or for a MapReduce transformation. I'm almost at the end. And now you see how it's beautiful because look at this query. Super simple, one line. I take a file, I navigate a little bit, open an array, navigate to foobar, and then I compute the sum. Very compact, except that this is also going to work if there's 1 trillion items. This is going to be done on the Spark cluster. And you see, if you actually would look inside, you would realize the JSON file is created as an RDD, navigation as transformations on RDDs, and then sum is just going to be a method call because Spark has an action that is able to, it's called reduce, that is able to compute, apply a sum or any binary operator to the sequence. So this works on billions, trillions, quadrillions of items in exactly the same way as it works with few items on your laptop. So what's the vision for this, where this is going? So now it's already 4 years ago, but things are moving very fast. Traditionally, people opposed, on the one hand, the good old structured systems, data warehouses, and so on. That's where the data is structured. relational tables, data cubes, and so on. So we have the systems for that, like PostgreSQL and so on, ETL. And then on the other side, there are the data lakes, S3, HDFS, and so on, where you just put the data in there, and then you use MapReduce or you use Spark in order to query it, right, on top of a cluster. And the two things were kind of opposed to each other, right? Either you have a system that is more like structured, or you have a data lake. It's either or. And so these people who actually, if you recognize the names, these are the Databricks engineers who are behind Spark, they suggested that we could merge the two together. We could have some huge infrastructure that has a data lake in there, except that it can be exposed in the same way as a structured system, part of it. And so they called it lake house. It's a contraction of data lake and warehouse, a data lake house, and that became a bit of a buzzword in the database community, which is the idea of having this huge system with a data lake. You can run structured business analytics efficiently. You can update the data. You can use machine learning analysis on top and so on. So it's called the data lakehouse. And so when you have a lakehouse like that, the vision is that a language like JSONiq or XQuery, which is its cousin for SQL, can be a good fit for a lakehouse like this. So that was the old way, and that is the new way where everything is just merged together in a single layer. I put there just a few slides of the performance comparison for RumbleDB. We compared it around, and the summary is that the performance is okay. Remember that it works on messy data. So what we want to show with performance is just that it doesn't degrade too much if the data is structured, right? It runs on messy data, but if the data is structured, the performance is still acceptable. So we run a few comparisons like this. Here with this slide, I want to show you that you can clean up data. So you know, whenever you want to run a machine learning algorithm, one of the challenges is that the data is not clean, and you need to clean up the data before you can put it in your machine learning pipeline. But the problem is that before JSONiq or XQuery, there was no language for that, right? If you want to clean up the data, you have no other choice than to use Python or an imperative language to clean up the data. But now you no longer need to, because a language like JSONiq or XQuery can read messy data. So you can use that language in order to clean up the data and then output a data frame. And the data frame is then your structured data that you can use as an input to the machine learning algorithm, right? So this is just an example of that. That's an example of a cleanup proposal. I'm just throwing that at you, but you can look at it offline. It's just an example of a file that is not clean because the name is sometimes an object, but name Pythagoras is then a string. And then you might want to clean up, for example, by saying that instead of having Spark just put everything in a string, you can just say, okay, if there's just a string, you put it in first, right? So this is what we could do to clean it up. And in fact, you can do it in JSONiq. That would be some JSONiq code that does that, that cleans up this messy data set into this highly structured data frame. But here you see, it's no longer a string. These are objects. It's no longer a string. These are arrays of strings, right? So this is all clean now, right? So look at this offline if you want, but this is just some code that allows you to do the cleanup with some reasonable and readable codes. And finally, there was a cool master's thesis a few years ago where a brilliant student, Jan, implemented machine learning in RumbleDB. So it means that you can create items that are in fact machine learning models, and you can fit them and then call them on some data, all within JSONiq. So it's not part of the lecture material, right? I'm just showing to you the sort of things that you can do. So this is a JSONiq query that actually fits a model on some data and then makes prediction. So this is called Rumble ML. Okay, so just as where this is going. The timing is perfect because this is my last slide. So what I recommend is do the exercises and train with JSONiq. There's plenty of notebooks available. There is a sandbox online on jsoniq.org. click on try it out. There's the notebooks that the TA is prepared. There is the textbook that contains the full introduction to JSONic. There's all the tutorials with which you can catch up if you did not do them during the semester. There will be JSONic at the exam, so really learn it. And once you have learned JSONic, you can very easily learn any of the other 30 languages. So whoever wins in 15 years, you'll be prepared for that. Next week, celebration, end of the semester, wrap up, quiz, no new material. It's just to celebrate. Tell all your friends to come. It's cool to have the quiz in presence. Usually we manage to have more people at the end of the semester. And then the nice thing is that if you win the prize, like chocolate, and then you can actually collect them if you're in the lecture hall. We don't know yet how to send them over Zoom. Thank you very much. Thank you, Zuming, for moderating the lecture. Thank you, everybody, for attending. Enjoy the exercises, and see you next week for the final lecture.